Have you ever used a car jack to lift a heavy vehicle? You might apply just a little effort and the car rises, almost like magic. But it's not magic, it's Pascal's law in action. Hi everyone! In this session, we are going to explore how pressure is transmitted in liquids and why this principle is the foundation of modern hydraulics. Liquids are nearly incompressible. So, when pressure is applied to one part of an enclosed liquid, it's transmitted equally in all directions. As shown in the diagram, if you press on one end of a U-tube filled with liquid, the pressure spreads out evenly across both arms. This transmission allows force to travel through fluids and makes hydraulics work. Let's understand the science behind this. So, what does Pascal's law say? It states when pressure is applied to an enclosed fluid, it is transmitted equally and undiminished in all directions throughout the fluid. That's powerful and elegant. Now, here's how we write it mathematically. P equals F divided by A, where P is pressure, F is force in newtons, and A is the area in square meters. If the pressure is the same in both pistons of a hydraulic system, we get F1 divided by A1 equals F2 divided by A2. This equation is key. It means we can apply a small force over a small area and create a large force over a bigger area. That's the heart of hydraulics. Take a look at the diagram of two pistons, one narrow, one wide, connected through a liquid. Pressure applied at one piston travels to the other side undiminished. Let's now apply Pascal's law to real machines. Imagine you apply a force on a small piston with an area of just 0.01 square meters. That force is transmitted through the liquid to a larger piston with an area of 0.5 square meters. Because pressure is conserved, the force on the larger piston is given by F2 equals A2 divided by A1 times F1, so the small input force gets multiplied. That's how hydraulic lifts, jacks, and presses work. You apply a small force at the input and get a large output force on the other side. In the diagram, notice how the small piston rises quickly while the larger one moves slowly, but with much greater force. That's force amplification through fluid pressure. Let's look at where you've probably seen Pascal's law in everyday life. Hydraulic brakes in vehicles, press the brake pedal and force is transmitted to the brake pads. Dentist chairs rise and lower smoothly using fluid-based pressure systems. Hydraulic presses are used in industries to compress metals with tons of force. Fuel injectors use high fluid pressure to atomize fuel into fine spray for combustion. In each case, a small input force is turned into a large mechanical output thanks to Pascal's law. Check out the visuals. From car lifts to industrial presses, Pascal's law is the unsung hero behind smooth, efficient operations. But wait, Pascal's law doesn't work in every situation. Here are the conditions that must be met. The fluid must be incompressible, usually a liquid, not a gas. The fluid must be enclosed completely, no leaks. The fluid must be at rest, no turbulence or movement. Any break in sealing, compressibility, or movement can violate Pascal's conditions. In the visual comparison, you see a properly sealed system where pressure is transmitted and a leaking setup where the principle breaks down. So, for Pascal's law to work, the system must be tight, still, and liquid-filled. Problem: in a hydraulic lift, a force of 300 newtons is applied to a small piston of area 0.02 square meters. The larger piston has an area of 0.5 square meters. What force is produced on the larger piston? We use the formula F2 equals A2 divided by A1 times F1. Substitute the values. F2 equals 0.5 divided by 0.02 times 300. That gives F2 equals 25 times 300 is equal to 7,500 newtons. so the lift exerts a force of 7,500 newtons on the larger piston. Visualize this with a labeled diagram, a small piston on the left applying 300 N and a large piston on the right outputting 7,500 N. That's fluid force amplification, made possible by Pascal's law. Let's wrap it all up. Pascal's law tells us that pressure in an enclosed liquid is transmitted equally and undiminished in every direction. This principle is behind hydraulic lifts, braking systems, presses, and even surgical tools. The key formula, F1 divided by A1 equals F2 divided by A2. It allows small forces to create large outputs, an elegant and essential engineering principle. So the next time you see a car rising in a garage or feel your bike brakes working smoothly, you'll know the physics behind it. I hope today's session helped you appreciate how pressure moves silently through liquids, shaping machines, transportation, and even life-saving tools. See you in the next lesson with another exciting concept in physics.